Hello, my name is Lucas Kinder. The title of my project is Qualitative Assessment of sUAS-based NDVI for Pipeline Vegetation Monitoring. Little introduction. Pipeline companies in West Virginia are required to have at least 70% of the pipeline covered with vegetation after construction is completed. Currently, pipeline inspectors walk a pipeline and have to visually inspect the total vegetation coverage. Areas of poor vegetation growth must be reseeded and fertilized. And I think new technology along with GIS analysis may allow for faster, more accurate inspection of pipeline corridor vegetation coverage. A little background. NDVI, or Normalized Difference Vegetation Index, gives an index value from -1 to 1 using the near-infrared band and a band in the visible red spectrum. Healthy green vegetation reflects more near-infrared light and absorbs more of the red spectrum of light, giving an NDVI value closer to 1. Inversely, unhealthy or dead vegetation as well as non-vegetative materials absorb more near-infrared light and reflect more of the red spectrum of light, giving an NDVI value closer to -1. And this is the NDVI equation using the red and near-infrared bands. As for my methods, a completed Arsenal pipeline corridor located in Harrison County, West Virginia was chosen. 10 sample locations based on visual inspection of vegetation coverage were chosen. 6 plots of good vegetation coverage and 4 plots of poor vegetation coverage. Each plot was polygonized using marking spray paint. The center coordinates and elevations of each polygon was collected using a Spectra SP80 GPS system. RGB near-infrared images were captured via a Centera 6X multispectral sensor attached to a DJI Matrice 200 V2 UAS flying an autonomous pre-planned flight. Photos were processed using Pix40 photogrammetry software. 2 ortho photos were created by stitching together individual pictures from both RGB and near-infrared bands. These are the 2 ortho photos. ArcMap was used to polygonize each of the 10 plots into shapefiles. The GPS points were added and used to georectify the 2 ortho photos. NDVI pixel values from each of the plots shapefiles were averaged to get a mean NDVI value for each plot. Good and poor vegetation NDVI value breaks were identified by analyzing the lowest value considered good vegetation, green, on the ortho photo, and the highest value considered poor vegetation, red, in the ortho photo. Each plot's mean value was then used to identify if the plot matched its visual identification of good or poor vegetation coverage. As for the results, preliminary results indicate that visual assessments of vegetation coverage on a pipeline corridor match the UAS-based NDVI data. Here you can see in plot 2, a square of green grass, and it shows up green in the NDVI ortho photo. And plot 4 was poor, really muddy, rocky soil there, and it shows up red in the NDVI. As for conclusions and future work, based on preliminary results, UAS-based NDVI data is a faster, more accurate way to assess vegetation coverage on a pipeline. Future research and experimentation should dictate NDVI's role in assessing total coverage of vegetation on pipeline corridors, how NDVI analysis responds to changing seasonal vegetation and light conditions, and why NDVI values within forested areas do not correlate with the same values seen in open areas, and etc. This undergrad research was funded by the National Science Foundation EPSCOR project, improving water management, treatment, and recovery in oil and gas production. And special thanks to Walter Velseca and Dr. Paul Kinder. Thank you.